Hello everyone, welcome to my video on the fundamental theorem of calculus part 2. So we saw the fundamental theorem of calculus part 1, which showed that there's a relationship between the integral and the derivative, namely that they're inverse operations of one another, which is great. But why do we love the fundamental theorem of calculus part 2? The reason being that it simplifies our life. It allows us to solve problems in a simple manner. We don't have to evaluate the integral with limits and Riemann sums by partitioning it into small rectangles and summing it up. We don't do that. We apply this definition, which we'll see is really simple. So the definition states that if f is a continuous function defined on a closed interval ab, so again we need continuity, then the integral from a to b of f of x dx is simply equal to capital F of b minus capital F of a. What's the capital F? Well, the capital F is the antiderivative of small f. So if you antiderive the function that's here, this continuous function, and then you substitute the upper bound and subtract it by the lower bound, that gives us the area. So let's go ahead and take a look at an example. So we skipped the proof for the fundamental theorem of calculus part 2. It's a simple proof, but if you guys are interested, let me know in the comments and I'll put that in a separate video. Okay, let's take a look at our first example. The first example over here, we have to find the area given this integral, the integral from 0 to 1 of x cubed dx. So if this looks familiar, that's because we actually solved this problem already. We solved this in the introduction video when we saw areas, and what we did is we took the the function x cubed, we sketched the function, and we considered the area under the curve on the interval from 0 to 1. Then we reduced the interval to a half, so 0 to a half and then a half to a 1. And then we found the upper bound and the lower bound of the area using the left endpoints and the right endpoint method. And then as we made the intervals of each rectangle smaller, we ended up getting that the area under the curve ended up being a quarter. So this was seen in one of the introduction videos. Let's go ahead and see the difference and how much easier it is to solve using the fundamental theorem of calculus part 2. So the first thing is x cubed continuous. You have to ask yourself, is this a continuous function? Well, x cubed is a polynomial, so it's continuous. We have continuity. We have a closed interval from 0 to 1. We're good to go. Let's apply FTC part 2. So it says to antiderive x cubed. So we have to take the antiderivative. You're asking yourself, what do you have to take the derivative of? What function do you have to take the derivative of in order to get x cubed? That's what you're asking yourself. So we're essentially using the power rule backwards, and we saw this again in the antiderivative videos, where the antiderivative of x to the 3, instead of dropping the 3 and then subtracting the exponent by 1, we add 1 to the exponent, and instead of multiplying or dropping it in front and multiplying, we divide by that value. So the antiderivative of x cubed is x to the 4 divided by 4, right? We add 1 to the exponent and we divide by whatever number we have in our exponent. And on the side, what you could do is go ahead and check. You could check if this is the correct antiderivative or integral. How? If we take the derivative, just side work, if we take the derivative of x to the 4 over 4 with respect to x, what do we get? Well, the derivative, we're dropping the 4 down in front, so we're going to multiply by the exponent. So we get 4 over here. We subtract the exponent by 1, giving us 4 minus 1 is 3, and we're dividing by 4. The 4's cancel, leaving us with just x cubed. So in the beginning, I strongly encourage you guys to check your work just to make sure you do have the correct antiderivative or the correct integral. Okay, so this is work you should do on the side just to make sure it's right. And the notation we use now is, there's two different notations you can use. We put a square bracket. The reason why we're putting the square bracket is saying that we still have to evaluate this from the upper bound and the lower bound. So 0 to 1, okay? This is one of the notations. I prefer the square notation, the square bracket notation. You could also put just simply a straight line and say that you have to still evaluate this from 1 to 0. Okay, so this is just notation that you could use. I'm gonna stick to these square brackets. So I put this in square brackets. We're gonna evaluate this from the lower bound 0 to the upper bound 1. And now we apply FTC part 2, which tells us to evaluate it at the upper bound. So this is like our capital F. So the rule was capital F of b minus capital F of 1. This function here is our capital F. It's the antiderivative. And our b is the upper bound, which is 1. So really, it's capital F of 1. And instead of, oops, sorry, that was supposed to be an a. The lower bound is going to be a 0. So we had f of b minus f of a. And now our upper bound is 1. Our lower bound is 0. So we just substitute 1 into this function, giving us 1 to the 4 over 4 minus 0 to the 4 minus 4. Okay, so you antiderive the continuous function that's given, then you put the upper bound into the, you plug in the upper bound and subtract it by the lower bound, giving us this, leaving us with 1 to the 4s of 1, divided by 4, that's a quarter, minus this thing is 0, and this was the same answer that we got in the introduction video. So this took, what, 3 steps? Whereas the other one took me, I think, a good 10 minutes to solve. So this is why we like the fundamental theorem of calculus part 2. This is very quick. So let's go ahead and look at a couple of more difficult examples. So in our next example over here, example 2, it says to find the area given the integral from 0 to 1 of 2 times e to the x dx. Let's go ahead and solve this together. So the first thing I noticed is that we have a 2 in front. We know if there's a constant in front of the function, we could pull it out. So we could write this as 2 times the integral from 0 to 1 of just e to the x dx. Okay. And now we're ready to integrate using the fundamental theorem of calculus part 2. So what's the antiderivative of e to the x? Well, before we ask that, we have to ask ourselves, is this function e to the x continuous? This is an exponential function, so yes, we have continuity. So since continuity is satisfied, we can now apply FTC part 2, and we ask ourselves, what's the antiderivative of e to the x? The antiderivative of e to the x is simply e to the x. So this is one of them that we like. So you have to make sure you have your antiderivative formulas memorized in order to answer these. So the antiderivative, I'm going to put in square brackets, is e to the x, and we're going to evaluate it from 0 to 1. So the lower bound 0, the upper bound is 1. Now we apply FTC part 2. We do f of b minus f of a. So I'm just going to leave the 2 in the front. And now we're going to do f of b minus capital F of a. Well, b is really just 1 in this case. It's the upper bound. And the lower bound a is just 0. So it's just capital F of 0. Capital F is the antiderivative, which we solved for was e to the x. The antiderivative of e to the x is e to the x. And what we get is 2, open bracket, e to the, we replace the x with 1, minus e to the 0. Okay. And this is simply just 2 times e minus e to the 0 is 1, and then when we distribute to get minus 2. Or if you want, you could factor out the 2 and leave this in brackets as 2e minus 1. And this is the final answer. This is the area under the curve of this integral. Okay, good. Let's keep going. So in the following example, we have to find the area given the integral from 0 to pi over 2 of sine x dx. So pause the video, give this a shot, see if you're able to solve it. So we start off by asking ourselves, is this function sine of x continuous? Well, we know what the sine function looks like. It oscillates between -1 and 1 forever, so the function is in fact continuous. So we could go ahead and antiderive sine. So what's the antiderivative of sine? Or what's the integral of sine? Well, we know the derivative of sine is cos, and using our pattern, sine, cos, negative sine, negative cos, so this pattern repeats itself. We know the derivative of sine is cos, but if we're antideriving, we're going the opposite way. It's actually negative cos, so be careful here. So this gives us negative cos of x, and we're evaluating negative cos from 0 to pi over 2. Okay, so I'm not going to write f of b minus f of a, but we're just going to apply it. So what's f of b minus f of a? Well, we're doing the upper bound, so minus cos of pi over 2 minus, and then negative, so be careful with negatives, cos of 0. Okay, so what's cos of pi over 2? You have to have your unit circle memorized. Cos of pi over 2 is 0. Right. So we had -0 minus negative turns into a plus, and cos of 0, again, from the unit circle, cos of 0 is 1. So this gives us -0 plus 1, which is just 1. So the area under the curve of sine x from 0 to pi over 2 is simply 1 unit squared. Okay, let's keep going. So in this next example over here, it says to find the area given the integral from -1 to 1 of 1 over x dx. So pause the video, give it a shot, see if you get the same answer as I do. So first things first, we integrate. So we have to remember the antiderivative of 1 over x. This is equal to, if you thought of using the power rule, then that's wrong. you can't use power rule because remember it doesn't work for the case when the exponent of the x is -1. Okay, so power rule doesn't work here, so be careful with that. This wouldn't work. So you have to remember that the integral of 1 over x, or the antiderivative of 1 over x, is ln of x. So here we're doing ln of x from -1 to 1. Now we're going to apply FTC part 2, and we're going to get ln of 1 minus ln of -1. These ln's are actually in absolute value brackets. So let's put that. Giving us ln of 1, which is 0, minus ln of -1 doesn't make sense, but since it's an absolute value function, it's actually +1, so ln of 1 is also 0, giving us 0. Okay. So if you got 0 as an answer, this is wrong. Okay. Be very careful. All this is incorrect. Why? Think about it. Think about why everything I did here is incorrect. Because in order to apply FTC part 2, the function you have over here in the integrand has to be a continuous function. Is 1 over x continuous? Well, no. This is a rational function. And we know that we cannot divide by 0. So if x is 0, there's an issue. And also what you have to check is 0 in the interval that we're talking about? Because if this is not continuous, but you have an interval, let's say, that does not include 0, then it's fine, because we're working on this interval. The interval that we're currently working on is from -1 to 0. Is 1 over x continuous on the given interval, on this closed interval here? No, it's not, because at 0, which is between -1 and 1, it's undefined. We're dividing by 0. So all this is wrong. You cannot apply FTC part 2 here. This is really important. Make sure when you're doing FTC part 2, you're dealing with a continuous function on a closed interval. Okay, so this is a big warning. Okay, so all this is incorrect. So the following example, it says to find the area given the integral from 1 to 9 of x to the 3/2 plus x minus 1, all that divided by square root of x. Integrating with respect to x. So pause the video, give this a shot, see if you're able to solve it. I'm going to go ahead and solve it now. We have a division. This is an issue because, again, we don't have any product rule, quotient rule for antiderivatives or for integrals at the moment. So right now, we don't know how to deal with this. But our game plan when we're taking the integral functions, deal with each term individually. Okay, so separate them. Since we have a division of a monomial, we could divide each term by the square root of x. So let's go ahead and do that. So we're going to set ourselves up the integral from 1 to 9. We'll think of it as x to the 3/2 over, I'm going to rewrite the square root as x to the 1/2 plus, every integral sign that you write comes with the dx. So I have to put dx here, plus, now the middle term from 1 to 9, x over x to the 1/2 dx, minus the integral from 1 over x to the 1/2 dx. Okay. Oops, sorry. It's a definite integral, so 1 to 9, we have to write our bounds of integration. Okay, so we set it up this way, and now we'll deal with each term individually. So we still haven't anti-derived yet. We're just going to simplify. So what's x to the 3/2 over x to the 1/2? Well, they have the same base, so we subtract the exponents. 3/2 minus 1/2 is 2/2, which is a whole. So here we have 1 to 9 of just x. Here, dx. The next one, we have the integral from 1 to 9, x divided by x to the 1/2. This has an exponent 1. We subtract the exponents. 1 divided by half is a half. So we have x to the 1/2 dx. Minus, here we have the integral from 1 to 9. And there's not much to do here. We could rewrite it as x to the -1/2 dx. Okay. So a question before you started that you should have asked yourself is this function here continuous? And the answer to that question is actually no, it's not continuous. Because on the bottom we have a square root of x, and that x, if you replace it with 0, we have an issue. We're dividing by 0 here. This is something you have to pay very close attention to. You have to be very careful. But in this specific problem, why is that a non-issue? Why is everything that we've done so far okay compared to the previous problem where it was wrong? Well, is 0 on the interval that we're talking about? No, because we're on the interval from 1 to 9. So this is fine. You have to ensure that the function is continuous on the closed interval that we're dealing with. So in this specific case, although we have a discontinuity at 0, that does not fall in our interval, so you're allowed to go ahead and apply FTC part 2. Okay, so pay very close attention to that, very important. If this was an interval from -1 to 9, then we fall into an issue and we cannot anti-derive. We cannot apply FDC part 2, okay? So keep that in mind. So let's continue and go ahead and solve the problem. Here, we apply just the power rule for antiderivatives. So we add 1 to the exponent and divide by that number. Adding 1 to the 1, we get x squared divided by 2, because you divide by whatever's in the exponent, and we have from 1 to 9. Plus, here when we anti-derive up 1/2, we add 1 to the exponent, so 1 plus 1/2 is 3/2, and then we divide by 3/2. And again, we're doing this from 1 to 9. And then lastly, we have this term here, separated by a subtraction. We add 1 to -1/2, giving us x to 1/2, divided by 1/2, again, from 1 to 9. 9 is the upper bound. So now we're going to substitute and apply FDC part 2 on each piece of the puzzle. So this gives us 9 squared over 2 minus 1 squared over 2. So it's still a bit long to do all these steps, but you're just substituting the upper bound and then the lower bound and separated by a subtraction. Next, you substitute the 9 in, giving us, I'm just going to flip the 3 over 2 as 2/3, because you're dividing by fractions, x, but instead of x, we're going to write 9 to the 3/2 minus 2/3, 1 to the 3/2. So here we're dividing by 3 over 2, which is the same as multiplying by 2 over 3. That's how we flip the fraction here. And next we have minus, again with the 1/2, I'm just going to flip it. It becomes 2 times 9 to the 1/2 minus 2 times 1 to the 1/2. And all this in brackets. Okay. So we separated. Let's deal with each term individually. I'm just going to erase up here to give myself more room. Giving us, here we have 9 squared divided by 2, that's 81 over 2. Minus 1 over 2, so minus 1 over 2. That's this piece here. The second piece here, again, without a calculator, this looks difficult, but it's actually not too bad. What we have really is, if we focus just on the 9 to the 3/2, let's do that up here. Always start with the root. It's easier, especially if you don't have a calculator. Dealing with the root first, or thinking of this as 9 to the 1/2, all that cubed, is the way to go. So instead of writing 3 over 2, the exponent is 1/2 times 3, and 1/2 is just the square root. So you're asking yourself, what's the square root of 9? That's simply just 3. And 3 cubed, we know, is 27. Okay, so that was this piece here. This piece here, the 9 to the 3/2, is just 27, and then times 2/3. Again, don't do 27 times 2 because you're working with larger numbers. Divide it by 3 first, it's easier. 27 divided by 3 is just 9, and then 9 times 2 is 18. Okay, so whenever you could take the root and whenever you could divide, do that operation first instead of cubing or squaring and multiplying. So to try to divide and make the numbers smaller, especially if you're working without a calculator. I think that's good advice. So that one's done, and then we have minus 2/3, 1 to the 3/2. The 1 to the 3/2 stays as 1, so we just subtract it by 2/3. And then over here, what do we have? We have 9 to the 1/2, so it's separated by a minus. 9 to the 1/2 is 3, 2 times 3 is 6, minus 2 to the 1, sorry. 2 times 1 to the 1/2 is just 2. Okay, so let's go ahead and simplify this. So the next step, 81/2 minus 1/2 is just 80/2, which is just 40. 18 minus 2/3, we'll deal with the minus 2/3 after. Let's deal with this bracket. Minus 6 minus 2 is just minus 4. And then here we have 40 plus 18 minus 4. So 18 minus 4 is just 14. And then we have 40 plus 14. So that's 54 minus 2/3. And here we just have to find a common denominator. So we're going to multiply 54 by 3. So 3 times 4 is 12. 3 times 5 is 15. Add the 1 is 16, so it's 162. So what we get is 162 minus 2 over 3, which gives us 160 divided by 3. Okay. And that's the final answer. So you might be asking, why how do we know if 160 is divisible by 3? Well, one of the divisibility tricks that you learn in elementary or high school is you sum the digits up and ask yourself if that value is divisible by 3. So 1 plus 6 plus 0 is 7. Could you do 7 divided by 3? No. So this value here is not divisible by 3. And this is our final answer in reduced form. Okay. So we get 160 over 3. Let's go ahead and look at the next example. So in the next example, it's asking us to use FTC part 2 to find the area of the integral from 0 to pi over 4 of 2 secant squared x dx. So again, pause the video, see if you're able to solve this on your own, and let's go ahead and do it. The first thing I'm going to do is remove the 2. That's a constant, so we can take it out. So we're left with 2 integral from 0 to pi over 4 of secant squared x dx. Okay. And now you're asking yourself, what's the antiderivative of secant squared? What function could you derive and the derivative is going to give us secant squared? Well, the answer to that is tan. So here we have 2 in the front. The antiderivative of secant squared is tan x, so you have to know your antiderivatives, and you're integrating from 0 to pi over 4. So we're applying FTC part 2. We're going to substitute the upper bound and subtract the lower bound. Let's go ahead and do that. So we have 2 on the outside. We have tan of pi over 4 minus tan of 0. Okay. And now we have to use our unit circle. If you don't remember what tan of pi over 4 is and tan of 0, rewrite it using the property that tan is equal to sine over cos. You don't have to do it this way. This is just if you don't remember the values of tan. This is an alternate way of doing it. And you could get it just by knowing this property that tan is equal to sine over cos and knowing your unit circle. Okay. So sine of pi over 4, we have the 2 that's sitting in the front. Sine of pi over 4 is root 2 over 2 from the unit circle, and cos of pi over 4 is the exact same thing, root 2 over 2. Minus sine of 0 we know is 0, and cos of 0 from our unit circle we know is 1. So what we have is root 2 over 2 divided by root 2 over 2. The same number divided by itself gives us 1. So this is just, let me just do it up here. We have the 2 on the outside, and in the bracket we have 1 minus 0 divided by 1 is 0. So we have 2 times 1, which is 2 units squared. Okay, and that's the final answer. Okay, so let's take a look at our final example. So our final and most complicated example is the integral from -1 to -1 of e to the x squared dx. So use FTC part 2 to evaluate this integral here. Pause the video, give this a shot. I'll give you a moment. So if you attempted this and you got the answer is 0, good job. So the answer here is just simply 0. How do we get 0? We cannot integrate this function. This is one of these functions, e to -x squared. We actually don't have any methods in calculus 2 to solve this. We could get it with approximations, but it's we can't use our integrating techniques to solve this. Okay, so this is actually not possible, what we know at the moment, and you're integrating from -1 to -1. So knowing that the bounds are the same, this is just simply using our properties. If the bounds of integrations are equal, in this case they are, the answer is simply 0. And we're done. Okay, so I hope this video helped. I hope you have a better understanding of fundamental theorem of calculus part 2. So remember, when you're applying it, make sure that the function is continuous. Make sure it's continuous on the closed interval AB. Okay, so take care. I hope this helped, and I'll see you in the next one.